Okay, so I want to talk about induced dipole interactions, because we haven't talked about what an induced dipole is. I guess I'll copy this and put it somewhere new. So what do you do for molecules that don't have a lot of polar character? Can they still engage in interactions? And the answer is yes. If it were not so, geckos would not be able to walk on walls, which would be unfortunate for Geico, I guess. I like the Geico commercials, but the ones with the gecko are not that fun. I don't think, anyway. All right, what is an induced dipole? Well, the idea is that the electron density around a molecule is polarizable and can adjust itself in real time to accommodate charges surrounding that molecule. So what this diagram is intended to show you is if this oxygen, which has a partial negative charge on it, approaches this, we're going to say is a nonpolar molecule, perhaps hexane. During the time when this water is close, with the oxygen oriented towards this molecule, the molecule itself can rearrange its electron density to accommodate the presence of this partial positive charge. It's shifting, and this isn't meant to indicate actual cations and anions. These are all delta minuses and delta pluses. What this is meant to indicate is that the molecule will distort its electron density so as to be complementary to whatever molecule is nearby. Okay? You might expect these interactions are pretty weak, and they are. Water, for example, if this molecule is huge, water doesn't mix with hexane. So presumably this interaction between a dipole and then an induced dipole is weak enough as to not be able to compensate for losing the hydrogen bonds that water has with itself. It's more complicated than that. We're going to talk about the hydrophobic effect a little bit later today. And here's a related situation. Here's a full-on cation. So we would call this an ion-induced dipole interaction. And again, the molecule is adjusting its electron density to accommodate the presence of a charge here. Let's see. And then lastly, if you have two such molecules, they can instantaneously adjust their electron density to be complementary to each other. And this is related to electron-electron correlation that we talked briefly about, but not a whole lot, in chapter 14. The idea that each electron is affected by all the other electrons in the molecule, and they can move in such a way as to minimize repulsion between each other and to maximize attractive interactions between adjacent molecules. So what I don't intend to say is this induced dipole is not permanent. One moment it's going to be like this, the next moment it's going to be like that. This is kind of like if you've ever seen fish swimming together in a school, or birds flying together in a mass, tiny birds flying together in a big mass. A couple of birds change their direction and then everybody does. A couple of fish change their direction and everybody does. In the same way, instantaneously the electron density is going to shift so that maybe, next nanosecond, picosecond, femtosecond, whatever, the negative charges or the partial negative charges are all over here instead of all over there. But when that happens, this molecule will also adjust itself so its negative charges are over here instead of over there. And this shifting back and forth and correlation of electrons can actually add up to be, it's individually weak, but it can add up to be quite a bit. You might imagine that that among the factors that might enhance these induced dipole interactions would be size. The larger a molecule is, the more, and the larger its surface area is, the more space there is for two molecules to get close to each other, and this induced dipole interaction depends on what's called contact surface area. Its distance dependence, if you look at the math, is highly dependent. No, is that an E or a? Yeah, that's. Its distance dependence is that may not be right. I don't even know. Is on 1 over r to the 6th. That means that you have to be really, really close for this interaction to matter. As soon as you increase a little bit, if you increase the radius by a factor of 2, the interaction decreases in strength by a factor of 2 to the 6th. Which is whatever, 2, 7, 4, 8, 16, 32, 64, yeah. All right, arithmetic, right? In order to have strong induced dipole interactions, the two molecules need to be close to each other. The greater the surface area that they can contact each other, the stronger the interaction is going to be. Also, polarizability is another factor, and it correlates with size. If a molecule is larger, it is likely to be more polarizable because there's more space to spread out its electron density. And if a molecule is able to do that more effectively, then these interactions can be stronger. Sometimes people call induced dipole interactions by a more familiar perhaps name, van der Waals interactions. These are often, well, sometimes also called London dispersion forces, and you can also call them induced dipole interactions. I tend to hear this one most of the time, but all right, and why did I say something about the gecko? Well, you've maybe heard or seen or read the story of how a gecko can walk on the wall and on ceilings was kind of complicated. People first hypothesized, well, the gecko must secrete some kind of adhesive from its limbs that allow it to stick, and it turns out no. It's just the structure of the gecko's foot pads are so intricate and have such high surface area. If you look in, well, should we look it up maybe? Let's see. Search for gecko. Foot microscope. All right. So we've got lots of fun images here. That's what it looks like to the eye. You can zoom in, and you've got lots of these. What happened? You can zoom in, and each toe is covered with this weird feathery thing, which itself has a lot of different, a lot of large surface area to it. And what happens is that this can push up against very close to a surface, and because there's the surface area, I mean, you may not necessarily know this, it's difficult to think about, but if you think about the surface area of a sphere versus, and we could encompass the same amount of space, but have a widely, I don't know, crenellated, variegated, whatever, folded back and forth surface. Surface area can be really, really huge here. And if you get that close to the surface, then the van der Waals interactions or the London dispersion forces or the induced dipole interactions between that surface and the gecko's foot are strong enough to hold the weight of a gecko. All right.
Dr. Price?
Yes?
The induced dipole interaction, can we also say it's dependent on contact angle?
Contact angle? Yes, I think. Well, I don't know. I don't know of a simple equation for that, though I've written some here from your text. They're not really important, and we don't need to worry about them, because I'm not going to ask you any questions about them. But you would, sure, I mean, you'd predict that the angle at which they contact matters in the sense that it would affect their surface area. So if you remember those benzene structures that we saw earlier, if we were ignoring the quadrupole part of that interaction, just imagine one benzene interacting with another like this. That's less contact surface area than if they interact like that. So I think the key issue is how close their surfaces and how much of the surfaces are touching. Right. Okay. Now, it's possible to misunderstand van der Waals interactions, and let me give you a couple of situations where people have done so. So imagine unfolded protein, and at some position, some side chains along the protein, you've got positive charges and negative charges. You have hydrogen bond donors, you have hydrogen bond acceptors, you've got non-polar groups, you've got polar but not charged side chains, right? And then presumably you've got this process called folding, wherein a protein adopts its specified conformation, and perhaps in this conformation now you have positive charges and negative charges interacting on the surface. Perhaps you have a hydrogen bond, perhaps you have a hydrogen bond between an amide nitrogen and a carbonyl oxygen. And then often the nonpolar side chains are sequestered in the interior of the protein. And they pack against each other quite tightly. And usually the free energy of folding is usually less than 0. That means equilibrium constant is greater than 1. That means folding is favorable, right? And it's tempting to, as I said before, not only to look at the charges and think, oh, that interaction must be important, but you have to consider, well, were there counter ions in solution that were already interacting with those charges when it was unfolded? Were there water molecules around that were hydrogen bonding with your groups when it was unfolded? So it's tempting to speculate that interactions that you see in the folded conformation are important for folding when it's possible they were decently interacting with other things in the unfolded shape. The other thing it's tempting to say is that the van der Waals interactions between non-polar groups in the protein are strong and drive protein folding. But there's a lot of evidence that that's not the case, in part because, of course, van der Waals interactions are pretty weak. So we need to talk about something that does explain why nonpolar functional groups tend to be on the interior of proteins, and also explains why water and oil don't mix. And we're going to call that the hydrophobic effect. Hydrophobic effect. When I first started to, I think in grad school, I thought the hydrophobic effect and the van der Waals interactions were the same thing. They're not. The hydrophobic effect involves water. Van der Waals interactions are present and they are a factor, but you cannot ignore water in biology. You've always got to be thinking about solvent, about water, and how it can perturb the system. So we're going to start by considering two different solvents. Let's consider water and maybe hexane. So here is our beaker, and it could be hexane, or I suppose it could be vegetable oil, whatever you want. I'm going to choose hexane because it's easier to draw. And even though hexane's colorless, we're going to shade this as though it were vegetable oil, just to remind ourselves that it's greasy. So this is hexane. Or we could make it 2, 4, 6, 8. We could make it gasoline. Let's just do that. That's fun. And then we'll make the other thing water. Oops. And we'll color this blue because of Rayleigh scattering that occurs. Anyway. So we've got a nonpolar solvent hexanes, we've got a polar solvent water. And they're not miscible with each other. If you mix them together, what you get is, depending on the density of the nonpolar thing versus the density of water, but I think we'll just say this is hexane or octane. Density is lighter than water. So what you would have is then two different phases. You'd have your hexane here, or octane, whatever, sorry, getting confused, and you'd have your water here. They don't mix with each other. And aside from oil and water don't mix and memorizing that, it's useful to consider why. Why is it this way? So let's imagine first the situation in which you have the situation that water's in when it's just pure water. All right. So in pure water, each oxygen is thought to be interacting with 3.5 to 4 nearby hydrogens. That means each lone pair on the oxygen is hydrogen bonding with another hydrogen from another water molecule. And I'm only showing you a static picture of this, and it's difficult to do because, of course, when do you stop drawing additional water molecules? And of course, each of these, and so on. And understand that this network is flexible and transient, and sometimes people call it flickering, in the sense that without a lot of change, you can trade who's hydrogen bonded to whom. That is, this hydrogen might now, as I think I've showed you, this hydrogen might now be involved in a covalent bond, and this one might be picked up by another water molecule. You get the idea. It's hard for me to show this fluctuating back and forth, but basically the network of hydrogen bonding in pure bulk water is very flexible, and that is one of the reasons why water is a liquid at room temperature. The kinetic energy that you have at room temperature is sufficient to allow individual water molecules to hydrogen bond with each other but not be held strongly in place for very much time. What does octane look like at the molecular level? Well, octane's also a liquid, so these interactions between octane molecules would be relatively weak. We're going to sort of show the cloud of electron density in the vicinity of this molecule is sort of like this. And as one octane molecule approaches the other, you could imagine them adjusting their electron density such that there's a little bit of negative charge on this side of the molecule. Oops, we want it to be even smaller than that. A little bit of extra electron density on this side of the molecule, and a little bit of poorer electron poorness on that side of the molecule. So this is just an induced dipole interaction. But those are weak, and individual octane molecules can slide past each other such that at room temperature you have enough kinetic energy that they don't really stay together. In both of these cases, because the interactions are weak, and because these molecules are liquids, you've got what's called high entropy, meaning there's a lot of disorder. That makes sense-ish? Okay. Now, if you mix them together, basically this allows almost all of the water molecules and almost all of the octane molecules to feel like they would feel if they were on their own. But now let's consider the alternative. Let's imagine the situation in which one octane molecule, 2, 4, 6, 2, 4, 6, 8, and here's its cloud of electron density. We're just going to dissolve one octane molecule in water. All right. So remember, the interactions that are available to water and van der Waals interactions would be dipole between water and octane would be dipole and induced dipole interactions, which again are going to be about the same, maybe slightly stronger, but not very strong. They're going to be weaker than hydrogen bonds, and about the same as the van der Waals interactions between individual octane molecules. All right, so but water molecules in the immediate vicinity of the nonpolar octane are going to be missing out on hydrogen bonding partners. In other words, in bulk water, it doesn't matter where you turn, there's always somebody to hydrogen bond with. But if you're immediately next to the nonpolar molecule, the way that you turn dramatically influences who and what you can hydrogen bond with. And so what happens for these water molecules in the immediate vicinity of the nonpolar molecule, they have to adjust their positions so as to maximize their opportunities for hydrogen bonding. This reduces their translational and rotational degrees of freedom, and almost makes it as though the nonpolar molecule were encased in a one molecule thick layer of ice. So I'm going to continue to try to draw that. But the point is that the water molecules in the immediate vicinity of the nonpolar thing that we're trying to dissolve in it lose hydrogen bonding interactions, and as a consequence, try to maximize their remaining possible hydrogen bonds. That causes the molecules close to the nonpolar, the water molecules close to the nonpolar group to slow down. And of course, molecules with lower kinetic energy are more rigid and less flexible. So basically, you encase the nonpolar molecule in an ice-like cage. I'm not really sure I've explained that well. It took a long time, but anything you want to ask about that? Okay, so in this layer, unlike in the bulk water, water molecules in this layer have lower entropy and fewer degrees of freedom, and they are moving way more slowly. Now, let's talk about what happens if we go from this dissolved state back to a state where the two are separated. All right, so take these two nonpolar molecules. Let's bring them close enough together such that they can interact with each other rather than the water molecules that are adjacent. Okay, if I bring these two close together, what happens to the water molecules that were here and here? Sorry. What happens to the water molecules that are here and here? They get out of jail free, right? So if I bring those two together, I'm going to have to do some erasing. Whoa. Had all of those go free. We had all of these go free. Oops. What on earth is going on there? Oh well. Sorry. So now you have a ton of water molecules that get released to the bulk. And I'm not sure how many we counted, but lots of individual molecules freed from the ice cage. They are back with lots of entropy. All right, and I think your text shows this with a figure that's maybe prettier than what I drew here. But yeah, your text attempt to show this is, here are your nonpolar molecules. Here's the ice-like cage that surrounds them. Here are the ones in between the two nonpolar molecules. If you bring those two together, all of these get released and their interactions don't have to be so tight, and they can go to having only maybe 2 hydrogen bonds per, or 1 hydrogen bond per oxygen, to having 3.5 to 4 nearby hydrogens per oxygen. So the hydrophobic effect is entropically driven. The reason it occurs is because water has a lower entropy when it's surrounding nonpolar things. So we're done, but going back to that protein folding story, it's not necessarily the strength of the interactions here that drives this. It's the fact that there used to be a bunch of cage-like water molecules surrounding the nonpolar side chains, and now they are free to be in the bulk. All right, so we'll talk more on Monday. Again, Friday's class is canceled, so have a great day and a great weekend, and I will see you Monday.